Hello everybody, welcome to our first video on Chapter 1. So Chapter 1 goes over the beginnings of quantum mechanics and where did it come from, why do we have it, what sort of experimental and theoretical results led us to realize that this is really how things work on the microscopic level. And so back in the late 1800s, physicists kind of thought they had mostly figured everything out about the world. There were great triumphs in understanding astronomy, right? Understanding the motion of planets, understanding electricity, magnetism, right? Many of these things had already been explained, by Newton, by Maxwell's equations and different things. And so late 1800s, physicists kind of felt like we've got it. We understand it. We understand the world, except for a few loose ends. And it turned out that those loose ends were actually really, really important. And this is one thing that excites scientists still today, right? That sometimes studying things that seem not terribly important, things like blackbody radiation that we're going to talk about, doesn't seem super relevant to our day-to-day lives. In fact, turn out to contain a lot of information about what's happening on a microscopic level. And to really understand it, we have to really understand what's going on behind the scenes. And so this is, the late 1800s, physicists kind of feel like they've got it. There's just some loose ends to wrap up. And some things that can't be completely explained by what we call now classical physics. So 3 of those we're going to talk about at the beginning of this class are blackbody radiation, that's the topic of this video, the photoelectric effect, that'll be the next video, and then hydrogen line spectra, which will be our third video. And so what is blackbody radiation? We'll start there. All right, so blackbody radiation. So blackbody radiation is what you observe in the case of, say, something like this electric burner here, where you have something that's, at a specific temperature, it emits light. And so a perfect blackbody source is something that is a perfect absorber and emitter of light. So absorbs and emits at all frequencies. So whatever color of light you have, your perfect blackbody will absorb it and then emit it with the same efficiency, we might say. And so some examples of blackbodies are like an electric stove, right? When it heats up, it starts emitting, even when it's at room temperature, it's emitting light, but we can't see it because it's infrared light. And so another example of blackbody source is the sun. Right, so the sun is approximately a blackbody source, and because it's hot, it emits lots of light, and that's what powers our world, right? And so blackbody radiation is a fairly important phenomenon. And so classical physicists, physicists around late 1800s, early 1900s, of course, were trying to understand this, and they were observing blackbody radiation and seeing, if they could observe kind of what are the general properties of blackbody radiation. So some general observations, if we scroll down here, we've got a chart here. Oh, all right, didn't want to zoom. Just want to scroll. All right. So now I want to zoom. Okay. So this is a chart showing blackbody radiation curves, experimentally speaking. So as we have curves, so the wavelength is on the bottom axis here. And so this is our wavelength of light. So going from longer wavelengths over here, so this is like the infrared region of the spectrum, up to visible where we can see, and then ultraviolet. Let's pick a different color so you can actually see my drawing. So at low temperatures, the peak of the curve, so say 3000 Kelvin here, low is an approximate, relative term here, so it's still pretty hot. But low temperatures, the peak is at longer wavelength, and then as we increase in temperature, the peak shifts further, to shorter and shorter wavelengths, and there's more light that's emitted. And so those are sort of the general properties that we see. And so classically there were physicists trying to understand this, and they came up with, based on Maxwell's equations and classical physics as we know it, they came up with an equation to explain this, known as the Rayleigh-Jeans law. And so their prediction is that the radiant energy density, so rho is a function of nu here, this is frequency, this is the inverse of wavelength if we're thinking in terms of light. This is going to depend on temperature, and it's a distribution, so we write this as, d nu here indicates small chunks of frequency. And so this distribution is given by this equation according to classical physics. 8 pi times Boltzmann constant times temperature over the speed of light cubed times the square of the frequency d nu. So this prediction says that as we keep increasing the frequency or decreasing the wavelength, because they're inversely related, the radiant energy should just keep increasing and increasing. So this is what's known as the radiant energy density. Or you can roughly think of it as the amount of light. How bright is it? So the radiant energy density, according to classical physics, should just keep increasing and increasing. And if we look at the prediction here, we see that it's okay at low frequencies or long wavelengths. But as we increase the frequency, it predicts that this should increase as the square of the frequency and never decrease. And so as we get to shorter and shorter wavelengths, according to this equation, things should just get brighter and brighter. And as we get to shorter and shorter wavelengths, we should just all be bathed in ultraviolet light constantly. And so this failure of classical physics to explain this is known as the ultraviolet catastrophe, which is, I think, would make a great band name if you're ever in the, want a physics nerdy band. The ultraviolet catastrophe is a good name. Right, so this prediction makes absolutely no sense and doesn't match at all the experimental observations that we see, that as you keep increasing experimentally, you'll reach some peak and it should go down, right? And that is not what was predicted classically. And so this disagreement indicated that, well, the classical prediction was completely wrong. And so the first successful model that actually explained this was derived by Max Planck. We'll hear his name quite a bit. But Planck came up with, in about 1900, he came up with this idea of a quantum assumption. So this idea, the classical idea, is that you can basically assume any energies, any frequencies of light are possible, right? So there's a continuous range of energies and frequencies. And what Max Planck said was that, well, actually, we'll assume this. We'll assume energy can only take on integer values of energy, of frequency, right? So he made this assumption that the energy can only take, there's some limit to the spacing between energy levels that you can have. So n here is an integer. H was a proportionality constant we now call Planck's constant. And nu here is still the frequency. So what this means, kind of, if conceptually speaking, is that if we kind of, write sort of possible energies that our blackbody can absorb and emit, classically speaking, this could take any possible value, right? So I'm trying to show this is a continuous range of values here, right? So you could have an energy of 1.1 and 1.1000001, right? Like it can just increase at any specific range. The quantum assumption that Max Planck had was that we have discrete energy levels that have some spacing. That's the integers that show up. So we have n equals 1, n equals 2, n equals 3, etc. And so if we make this assumption, we get a different equation than the Rayleigh-Jeans equation. So we instead get an energy density as a function of temperature that looks somewhat similar, 8 pi, but now we have this Planck constant show up, over speed of light cubed. And then we get this e to the h nu over Boltzmann constant times temperature minus 1. And so if we fit this equation to the experimental data, we can determine what the value of h is, and Planck got that h is approximately equal to 6.626 times 10 to the minus 34 joules times seconds. So we can also switch this to wavelength and get, the wavelength version of this, which sometimes is more useful depending on what we want to do with it. You get the experience just like in class where I write things down wrong the first time. So switch this to wavelength and we get 8 pi h c over lambda to the 5th d lambda e to the hc over lambda kb t minus 1. So this is the same equation. If we want to know where the maximum in the distribution is, we can take the derivative of this equation, set it equal to 0 to find the max, and we get that lambda max times temperature is equal to hc over 4.965 times the Boltzmann constant, or we can just multiply out those constants on the right-hand side of the equation, and we get lambda max times T equals 2.90 times 10 to the minus 3 meters times Kelvin. So this is the first example that we're talking about in this class where this quantum assumption shows up, where the only way to explain this is to assume that we can't take any possible values and that classical physics can't completely explain this, right? And so if we go back to this diagram here, these curves that are drawn here, these are actually based on the Planck distribution that we just looked at. So it describes the blackbody radiation perfectly. So this assumption that Planck made, he treated it just as sort of a mathematical necessity to make the math work out. He didn't really believe that this necessarily was the way the world worked. It was just something to do to get the math to work out and for this to work. So that's our first example of something that couldn't be explained by classical physics and required a quantum assumption to make things work out.